Okay, we're gonna start. This is our last day, and I'm honored to be the chairing this morning session. Our first speaker today is Frank Nielsen. Frank Nielsen is one of the organizers of this week, even if he couldn't be here physically. He's a professor at Ecole Polytechnique, as well as associated to the Sony Computer Science Lab in Japan. And his talk will be about information geometry and distances, computational perspective with application in machine learning. Okay, shall we start?
Okay, thank you, Luigi, for the nice introduction, and let me thank all the participants to this event. So my plan was to come and to be with you during the full week, but unfortunately, because of regulation, if I leave Japan where I am now, I cannot re-enter Japan, so it's not possible to be physically participating at this meeting. So we have this remote session today. And I hope you will enjoy it, and if it's too long, we can make breaks. So I changed a little bit the title of the talk, and it will be very general about distances of information geometry, and I will emphasize computational aspects of it. So the outline of the talk is mostly 3 mini talks that I stitched all together. I will first start by some geometry on bounding complex matrix domains that I will call the Siegel-Klein geometry. Then I will focus on more information geometric structures on a special manifold, and we will see why it's very special manifold compared to other location scale families. And if time allows, I will spend some time to present some generalization of one renowned divergence in information sciences, which is the Jensen-Shannon divergence. Okay. In case my connection is broken or if the sound is not so good, please interrupt me or let me know. I just see now my full screen with the slide, and I do not have any feedback. So I will continue to talk unless you let me know that there's a problem. Okay, so let me start with the first part of this talk, which is about Hilbert geometry for the Siegel disk domain. And this geometry on the Siegel disk, I will call it Siegel-Klein disk model. So if we have a quick look at hyperbolic geometry, where there exist several parallel lines to one given line, there are several Riemannian models of this hyperbolic geometry, and some famous ones are the Poincaré half space or the Poincaré disk, which is conformal so that it preserves the angles with the Euclidean angle. And another useful model is a non-conformal Klein model, where the angles are not preserved, but where the geodesics are straight Euclidean lines, which is very useful for computation. And here on the right side, you can see that there is also the Beltrami half sphere model, or there's a hyperbolide model here in purple. So there's a nice animation here where you can visualize the Voronoi diagram in hyperbolic geometry using these 5 models. I said that this is a Riemannian geometric models because if you look, for example, in the Poincaré disk or in the Klein disk, I visualize here the metric tensor as a small ellipsoid, which is a T-centric matrix. And in the Poincaré disk, you can see that it is more or less like a Euclidean shaped balls, which shows that it is conformal. And here you can see that it's deformed ellipsoid, which shows that it is non-conformal except at the origin. Okay, so what is Siegel geometry? The first model of Siegel geometry is what we call the Siegel upper space. And actually, the title of the paper by Siegel in the 1940s is about symplectic geometry. So today, symplectic geometry is more or less related to symplectic manifold. But in that case, it was more related to complex matrix groups and the geometry of an extension and generalization of the Poincaré upper space. So the Siegel upper space, SH here, is a set of d times d complex matrices, which can be decomposed as x plus y plus I y, where x is a symmetric matrix and y is a positive definite matrix. Okay? And Siegel in the 1940s defined the infinitesimal length element by this formula here, and reported the geodesic Riemannian length distance here as this expression. So we have the square root of Ri, where Ri is if a real eigenvalue of this quantity here, R of Z1 and Z2, which are the two complex matrices from which we want to compute the Siegel distance. And we compute the equivalent of what is the matrix Roche ratio here. And although the matrices are complex, R is having all real eigenvalues, but it's not Hermitian. So it's very remarkable formulae. And when you compute it in practice, what you need to do is to round the eigenvalues, because you have very small values for the imaginary parts, and you need to round it to 0 to get real eigenvalues to apply this formula. This is a computational practical aspect of it. So this Siegel upper space actually also generates a cone of positive definite matrices. So here I will call the definition of the Siegel upper space, and this was the Siegel Riemannian metric. And you can see that if you put the x to 0, and what you end up here is the usual Riemannian metric for the cone. And you recover also the distance between two positive definite matrices on the cone as follows. Okay, so Siegel upper space geometry generalizes the Riemannian geometry of the positive definite cone. And also, of course, as I said earlier, it's a matrix generalization of the Poincaré upper plane, because if you choose a dimension of your complex matrix to be 1, you have complex numbers. And if you plug the formula, you will get something that is equivalent to the hyperbolic Poincaré disk distance. The distance is the hyperbolic Poincaré. Okay. So now we are going to make some connection with studying the isometry, and for doing so, we generalize what is called linear fractional transformation for the Poincaré upper plane. So we consider symplectic maps here, which are generalized Mobius transformation. So we are giving a 2D by 2D matrix S, which is a square matrix, block matrix with A, B, C, D. And you define for a complex matrix Z this transformation that you can see as a generalized matrix Mobius transformation, okay? Phi S of Z. And the set of admissible matrices S shall have a very particular structure. It shall be satisfying this equation here. Do you see my mouse pointer when I speak, by the way? Hello?
Sorry, with Isabel. Yes, we see it.
Oh, so when I move my mouse, you also see it, okay?
Yes, we see everything.
Okay, thank you. So here you have the constraints on the block matrices here, and you can define the group inverse as follows. So